start with a very simple problem, 1D problem, and then we will generalize to the 3D case using the tool that dell'Isola has shown in the previous lecture. So the idea is the following: we have a bar. We can, since we have, we want to deal only with the one-dimensional case, the external action will be imposed only in this direction. We can say that this is the frame of reference, this is the versor, the unit vector, and okay, we can say that this is an abscissa, so it gives the coordinates, and these coordinates will arrive from 0. The range of this coordinate is from 0 to L. So the internal energy, it depends upon what. So we have that a certain particle that has an abscissa capital X will be transposed in one particle in a different position called small x, that will be T of X. This can be also expressed in this way, where U is the displacement. So small x is capital X plus something, and this something is a displacement. So this is another form to express the placement function. Placement is equal to x plus displacement. And the internal energy can be seen as a function of K prime or of U prime. Let us assume to write, okay, but it's not important, this definition of displacement. Just assuming, because you remember that the dell'Isola, maybe here in this Greek, no? Called that E was a function of F, and F is the gradient of K. In 1D case, F is exactly K prime. Do you have this in mind? You see this similarity. This is the derivative, the gradient of a vector that is a tensor. But in 1D, you can make the derivative only in one direction, and you have only one component. So we have only this. Let us see now. This is the density of energy. In order to find the total internal energy, you have to make the integration from 0 to L. But this is represent only the internal energy. If we consider some external action, possible external action, with maybe force, what one can think about force. This force can be distributed, and we can say that this is in this reasoning is considered in this way. This is D n because it's normal U, and then one can say. So we consider only consider from the external world, we consider only something that is proportional to u. You can also consider more different external action. Then maybe we can go a little bit more inside this in this stuff, but at the end of this lecture. So, but the external action can occur not only in the interior of the body, but also in the exterior one. Maybe here we can say F0 U F0 plus FL minus FL U of L. If we call this an action, so the action is due to the internal part and the external part. The external part is due from a volume part, so a part, something distributed over the volume, or at the border. U is the displacement. You see that we look at the displacement because this is a work. So we can to have a work, we have displacement multiplied by something from the external world. That generally is called force. This is the reason why I use the letter F. F in 0. This is F in L. But F in L may work on the displacement at L. And this is a different dimension with respect to this F, because this is a force per unit length. Now, if we want to get the equation of motion, so the deformation, we have to evaluate the variation of this action. The variation of this action can be, what does it mean? Well, so the action is a function of this placement, The variation of the action is nothing else than the action evaluated at the displacement plus something minus the action at t. And this can be evaluated simply making the derivative. So since the integral is done over a fixed volume, we can evaluate now the variation of A, inserting this symbol inside the integral. And here we can say the integral from 0 to L of the variation of E minus, let us assume that Bn is something from the external world, so it has nothing to do with the displacement, so we can say that it is independent of displacement. So we have Bn delta U, dx, then minus F0 delta U at 0 minus FL at L. Of course, this is a there is a there. So this can also be looked at the following form. You can say that this is the derivative of epsilon of E with respect to what? So what is this E is a function of t prime, so this is can be seen in the following ways. The derivative of E with respect to t prime multiplied the variation of t prime. Minus dn delta u. Delta u, what is it? From here, delta t is equal to delta x plus the delta u. But delta x is 0 because you don't vary x when you make a variation, because you vary only t. So delta t is equal to delta u. That means that here we can have delta t and so on. This is minus f0 delta t in 0 minus fl delta t at L. This is a standard procedure because now we want to have a delta t multiplied something, and then say, look, we look for an equation that is valid for every variation, so for every delta t, and then we can make 0 what delta t is multiplied if you want to assume the delta, the variation of the action. So how to get rid of this prime? Simply remembering that if you have two functions fg and make the derivative, this is equal to f prime g plus fg prime. So fg prime is equal to fg prime minus f prime g. That means that here we have the integral from 0 to L of the derivative of both prime minus the derivative of both minus f prime g. That means prime delta t. And we can substitute this part. Now you remember the famous theorem in which you have the integral of a derivative, so we have to calculate this at L minus this at 0. Say instead of this part, we can say that we have derivative of E with respect to T prime delta t evaluate between 0 and L. That means this, we evaluate this at L minus this at 0. And we have this part. Rewrite this calculation in the following way.
Sorry, may I ask a question?
Yeah.
Can you tell us one more time why the delta t is the same as delta u? One more time.
Yeah. what means variation? You have a placement, maybe this is x and this is t. Let us assume that we have displacement. And then you evaluate the variation of displacement. That means that you take into consideration a function different from this. That is maybe like this. So what you vary is only the fundamental field, that is the placement. If you vary the placement, you vary of course u, because they are related, but you don't vary x. Because you vary only the function. Because the idea is to have a functional, this is a functional, this case is a function that depends only upon the fundamental fields. In this case we have only placement as a fundamental field. If you have done the theory of M&MoCS theory, maybe you have used this. You have as a fundamental field, you have not only the placement, but you have also the rotation of the section. In this case, we have only placement. And so you have to vary only that field. That means that x is the same. So this is an important thing, that x is the same, but not capital X is the same, not small x. Because small x is capital X plus u. That vary only in the zero. Yes, about the rest. Yes. Okay. So here what we have that the variation of a equal to 0 equal to what? The integral from 0 to L of delta t multiplied by this part, so minus Bn, and this part, that is minus the derivative of t with respect to t prime, dx. And then we have, this means this evaluated at L, so we can say plus delta t evaluated at L that multiplies the derivative of t with respect to t prime at L. Minus FL. So we have taken into consideration this part and this part. Now we have to take into consideration also this other part. That means plus delta t at 0. And here we have minus evaluated in 0. So this evaluated in L minus this evaluated in 0. So now let us see our problem there. If we now imagine a real problem. In a real problem, your bodies are constrained somehow. This chair has a constraint at the bottom. This blackboard has a constraint at this border. That means that the placement cannot vary in reality arbitrarily, because they have some restriction. You have to impose some restriction. Otherwise, your equations are not related to your problem. If the variation are not arbitrary because they are constrained at some point, then this must be taken into account. For example, if you have a bar and this part is constrained and this part is excited somehow, maybe this effect, eventually this can be 0, but can also be different from 0. This means that the placement in 0 is constrained to be 0. Even if you impose here a displacement, a fixed displacement, maybe this fixed displacement is A. Then, anyway, the variation at 0, if you impose something at this border, the variation in 0 is always 0, independently of this value. This means that this part is 0. You can erase this for this particular problem. But this part you cannot erase because the variation in this point is arbitrary because you don't have a kinematical constraint. So the only thing that you can, in which you can get rid of this part, is to say that the derivative of epsilon with respect to t prime at L is equal to FL. So we have a relation in L of this form. And this, in the interior of the bar, you don't have restriction on delta t, so you have to assume that this is equal to 0 if you want this. And so you have this other part. This is evaluated in L, and so the other is this one. Prime plus bn equal to 0, and this is for every x. So you have this one, that is your differential equation. In 3D will be partial differential equation, you will see, and then a boundary condition. That is not only this boundary condition, but also this one. So we have two boundary conditions at the two border. This condition can be kinematically defined or dynamically defined. If you impose some constraint on your placement, it is directly the boundary condition comes directly from your restriction. If you don't impose anything on the kinematics, the boundary conditions that you have to impose are calculated. Is this one, exactly this one. For example, if you say that this epsilon is equal to 1/2 k u prime squared, this means that what is the derivative of epsilon with respect to t prime? This is equal to the derivative of e, the non-natural of e with respect to u prime, multiply the derivative of u prime with respect to t prime, that is 1. Because u prime and t prime, the derivative are the same. Okay? That means that there the internal equation are so you have the derivative of this then this is equal to k u prime. If k is constant, the differential equations are simply k u second plus Vm equal to 0. And at the border you have u in 0 equal to 0, u in L. How to get the u in L? You don't have in fact u in L in this case because the boundary condition is there. The derivative of E with respect to t prime is k u prime. So in fact, okay, you have k u prime evaluated in L equal to FL. So you have derived your boundary value problem. Question? Maybe you have also seen this simple problem in your career, isn't it? This is a bar that you pull or compress. In the three-dimensional case, the procedures are exactly the same. The only difference are the following. The first difference: the border is not composed only by 2 points, but you have a surface. The fact that you can apply kinematical restriction on 1 or 2 points is transformed in a 3D case into the fact that you can apply some kinematical constraint on a part of your surface or your border, or on the border, on the wall of your border. For example, again, if you have this chair, you have a restriction only in the bottom, in the surface that are in contact with the palm. But in this part, you don't have any restriction. In this computer, you have a kinematical restriction only at the border, at the bottom, but in this part is free. That means that you have no external force. This F will be 0 here. Maybe you should consider the weight of this computer. That means that you have some external force, but not concentrated at the border, but distributed over all the volume. And if I push in this computer on this part, it means that I don't have a kinematical restriction here, but I don't have a 0 external action in this part of the border, but I have something at the border of it, not in all over the volume. And what are this is the first difference. The second difference is that your kinematical field T is not now a vector, is not now a scalar, but it is a vector, so it can have every direction. The derivatives can be done in any direction, so F is a tensor. So the vector notation is the index notation. But this action is, let us see how to change this action in a three-dimensional case. Here we have only the result. So I can also erase this. So in 1D, we have said that the action was the integral from 0 to L of E prime minus E and U minus F0 U F0 minus FL U FL. This we have done. This is 1D case. In 3D case, we have not an integral from 0 to L, but we have an integral on a certain configuration. In your opinion, this configuration is the referential one or the present one? We have our potatoes that is deformed somehow through the placement function key. This is the point at capital X, this is small x. Before we have a bar, the length of which was L, and at the end maybe you have you have a bar, the length of which, who knows, it depends upon the force. If you take an elastic material, you pull, the length is different from L, from the initial length L. But we have used the integral from 0 to L. So here we have a referential configuration and a present configuration. We have to make an integral here in the reference configuration and in the present configuration. You have to have an integral over a domain that you know. You know the reference configuration. You don't know the present configuration. In fact, the present configuration is the solution of your problem. When you have a solution, when you know each point, how each point are displaced, then you know also the final shape of your body. At the beginning you don't know, so the only possibility here is to use an integral over the reference configuration. And here we have the energy of F, that now is a tensor. F has some index. Let us use Fij is equal to the derivative of Ki over Xj. That means that the component 1 is equal to the derivative of Q1 with respect to x1 and so on. For all the 9 components of this tensor. In fact, I should say all the right components of this matrix in a certain frame of reference. So here is minus the external action. Now here we have used a part that is inside the domain and a part at the border. So we can say that inside the domain we can use an external energy or okay, let us see it this way, and then this is the volume, and at the border the integral over the surface of something. Let us find here, let us use here fx. Then we will particularize this accordingly, because you see that here the external part we have decomposed into this part, Bn u. So maybe also this we have to decompose it the same way, and also this. Let us see how to do. So we can now evaluate the variation of this. The variation of K in the 3D case. the variation in the same way as we did before goes inside the integral, the sign of integration, and we have the variation of E, that is a function of f, minus the variation of ex minus the integral over the surface of the variation of fx. This we keep this part. What is the variation of E? The same way as we did before, this is the derivative of E with respect to f multiplied the variation of f. In index notation, this means that you have to make here the index here and the same index here. It means that here you have sum over the indexes I and j. This means derivative of E with respect to f11 multiplied delta f11 plus derivative with respect to f12 multiplied delta f12 and so on until you saturate both indexes. So we have now 9 alternates. But this what is it? This is the variation of the derivative of I with respect to xj. So we can put inside this symbol of variation, we can say that this is the derivative of the variation of I with respect to xj. So here, instead of write delta fij, we can replace this. So the derivative of the variation, the I component of the variation of replacement, derivative of this with respect to xj. But this is also equal for the same rule that we have used before. You remember, I said that fg, the derivative, is equal to f prime g plus fg prime. We have used this simple rule that use the same here. So we can say that this is equal to the derivative of xj of both minus the derivative of this part. Derivative with respect to xj delta here. You see that I use this trick because now I have an integration over d star of delta E, but a part of this is the derivative of xj of something. So we can use the divergence theorem. Before we have used, in the 1D case, we have used this. the integral of f prime over in dx is equal to f in L minus f in 0 in the previous case. Now what we use the fact that the integral over a domain of the divergence of a certain vector f in the volume, this is equal to the integral over the surface of this volume of f scalar n in the surface. Do you know this state theorem? Have you ever seen this theorem in the calculus course? This theorem you know. This is you can say that it is a generalization of this theorem for the 3D case. It is a very important tool in continuum mechanics because you can transform an integral over a volume onto an integral over its surface. If the integral over a volume can be written as the divergence of a vector. What is the divergence of a vector? This can be seen in this way. This is the integral. This is equal to the derivative of the I component of f with respect to xi. The index are repeated. That means that this is the derivative of f1 with respect to x1 plus the derivative of f2 with respect to x2, and so on. In the volume. Now, in this case, you have here not, I mean, if I use the symbol I, or I use the symbol Tom, Jerry, or J, the same. The importance is to know that this symbol goes from 1 to something. We are in 3D case, so it goes from 1 to 3. And you see that your fj is nothing else than this. Do you have a question? Do you have a question? No. And this is equal to this. That means that this is equal to the derivative to the integral over the surface of fi and I in ds. Because this scalar product is the scalar product of this function over the scalar product of this function and the normal vector. You take the surface is characterized by its external normal, and this external normal vary over the surface, and this means that this integral depends only on the external normal of the surface. Now, this I used. Now I can say now that so the variation of this action in 3D is equal to the integral over the star of this. That means that the integral over the surface of this multiplied by ni or nj. I mean, this I, because here I have the repeated index over I, so I can even here I can change the symbol from I to j, so that fj is this, and this is my fj in the application of this theorem. this is equal to the derivative of E with respect to f ij delta ti, that is our fj, that is this one, multiply nj. I call this n with a capital letter. Why? Because if I use this here, if I use here the reference configuration, which we must, generally the normal vector in the actual configuration is small n. In the reference configuration is capital N, as far as the capital X and small x, in the same way. And this is in the surface. And then we have also the other part, that is minus the integral over the star of this part. So we have delta Ei multiplying the derivative of E with respect to f ij. No. This part, the derivative, use the derivative over xj. This is the derivative over fj, the derivative of E with respect to fij, and delta ti. This is delta ti. Now, if now we say that this part is nothing else than the scalar product of delta t and certain b vector, these are both vector, that in index notation we can say I and I. You see that here is replaced with this. This is minus bi. Okay, we include this part. Another part that we need now is this. Now again, if this is replaced by delta t scalar product f, maybe let us call this t, tx, that in index notation is ei txi, sum over I. In order to take into account this part, of course this is an integral over the surface, so this is in the S. Here we have minus the integral over the surface of delta ti P external I. You can see that you can put together these two terms. I erase now the divergence theorem or Gauss theorem. And we can say that now that this ds can be put a little bit far away with delta ti. I insert here delta ti, so here I have to erase. this nj I put near here. And now I can say that this is minus tx I parenthesis, and I have the rid of this. Now the reasonings are the same as before, because we have our potatoes there. We have some external action. Here the external action can be included into two parts, can be classified into two parts. The kinematical parts, so maybe we can say that the border of our domain can be split into two parts. Kinematical part and dynamical part. In the kinematical part, you impose some external constraint. For example, in this computer, in the bottom, the displacement in the bottom is fixed or imposed somehow, but fixed. This means that in that part, this delta key is 0, because the displacement cannot vary. So this is 0. So we cannot say that this is 0. In that part, we say that the displacement is fixed and imposed from the beginning. In the other part, everything is free. That means that the external action is 0, except for that surface on which I have pushed the computer. Because in that surface, this Tx is different from 0. And so this part must be different from 0. In the other part of the surface, this part is 0. So you can say that if this kinematical part delta key is 0, you can say that this part is this surface integral is the sum of two integrals, those in the kinematical part and those in the dynamical one. In the kinematical part, this is 0, so this part cannot be considered, and we have only the part of the surface on which we do not prescribe any kinematics. So the free part and the part on which I have pushed. And so the partial differential equation are the following. We have the derivative with respect to xj, the derivative of E with respect to fij minus bi equal to 0 for every x. And the rest is this one, so the derivative of E with respect to fij and j is equal to px I. And this is for every x belonging to this part. So the surface, the dynamical part of the surface. So this is the system of your partial differential equation. Let us see now an example that is remarkable. For example, the linear elastic material. No, linear elastic material. Can I do this? the internal energy E, you have seen with Francesco dell'Isola that it's true that E is a function of F, but in particular it is because you have to exclude the fact that a rigid body rotation can influence this internal energy. You have only that this is a function of C, where C is equal to F transport F. No, F transpose. Let me see. No, F transpose F. So that, okay, it's this one. What does it mean? It means that this equation, dE over dF, must be changed a little bit, because from this assumption, what do you have? You have that the derivative of E with respect to Fij is equal to the derivative of E theta with respect to Fij. That means the derivative of E theta with respect to C AB multiply the derivative of C AB over Fij. This is the chain rule of the derivation. If a function is a function of C that is a function of F, the derivative of this E with respect to F is this one, where you have to sum over all the function, the intermediate function. So you have to sum over A and over B. In this notation, you say that this is the sum of non-term. AB equal to 1, 1, 1, 2, 1, 3, 1, 2, 2, 3, 1, 3, 2, 3, 3. So it remains to calculate this part. But what is CAB? Is this hence this matrix and the component AB. But this means that this is the matrix F transpose AI multiplied the F EB, because we have the row by column product. If you have two matrices, you know this? Have you done with this one? If you have two matrices, this matrix F transpose, this matrix F, you want to calculate the component AB, this is equal to, we have to do the row by column product. That is this with the sum over I. However, if F transpose component AI is the same as we say F in the component IA. And then if I call instead of I call H is the same, no? Because I call it Tom, Jerry, or something different. I can call it H. Why I say this? Because now I have to calculate this part. So I have to calculate the derivative of CAB with respect to Fij. And this is equal to what? Is equal to the derivative of this with respect to Fij multiplied by this, plus this, the derivative of this. It is the rule of the derivation of a function. So this means that this is the derivative of F HA with respect to Fij HB plus FHA, the derivative of F with respect to F. So the derivative of FHB with respect to Fij. We've done the derivative of this multiplied by this plus this multiplied the derivative of this. But these are the same tensor. So this derivative is equal to 1 when the component is the same, and 0 when the components are different. That means that this is equal to, in order to represent this tensor, you can use the delta, the Kronecker delta. So these components are the same only when H is equal to I and A is equal to J. And you have evaluated this. When the first index is the same, this is equal to 1. But also, the second index should be the same. In all the other cases, this is 0. And so you have to say here FHB plus FHA, this one, that is the same rule, delta HI, delta BJ. You see now, here we have a sum over H. Sum over H means that H should be equal to 1, 2, and 3. But this sum is 0 when H is different from I. So the only index of H that survives is that index that is equal to I. So from this we have to say delta AJ F instead of H we write I B. And here the same, we have the sum over H, but the only symbol that survives is I. So plus F IA multiplied delta BJ. So this is this one. No? So let us evaluate now this. So now we have the derivative of E with respect to Fij equal to the derivative of E theta with respect to CAB multiply the derivative of CAB with respect to Fij. That is this one, that is this one. So, parenthesis, delta AJ FIB plus FEA delta BJ. So now again, we have a sum over A and a sum over B. So the sum, let us see the sum over A. This is equal to what? To the derivative of E with respect to A will survive only when A is equal to J. So C J B FIB plus the derivative of E with respect to what? You see that the sum now survives only, it is with respect to B, but it survives only when B is equal to J. So AJ, C, AJ, F, I, A. Now have a look on this term. The sum is with respect to B, but B is a repeated index, so it can change the name. It can be called Jerry, it can be called Tom, it can be called A. Let us call it A. Moreover, C is a symmetric tensor, because do you remember that C is equal to F transpose F. So the transport of C is equal to the transport of this multiplied by the transport of this. The transport of this is F transport. The transport of this is the transport of the transport of F. That is F. That means that C is symmetric. If C is symmetric, you can change the order of the indexes, and the result is the same. That means that here you can say that CAJ is equal to CJA. And now you discover that these two terms are the same. So you can put 2 here and erase this part. It means that this part now can be changed accordingly to this. The important thing that I have to mention is that this is a tensor. This is a tensor that is called Tij, and this in the literature is called first Piola stress tensor, or first Piola Kirchhoff stress tensor. I have some videos to give an example. What is the time?
1 meno un quarto.
Meno 4, so io. So. So if we recall this in terms of that tensor, we can say the following: that the partial differential equations are the derivative of, with respect to xj of what? Of Tij here it is a minus, but maybe there I made a mistake. It's not a minus, it's plus. Let us check here. No, I've lost the calculation. This should be 0. It should be plus. It is a question of what you define at the beginning as Pi. equal to 0, where for every x belonging to B star, and at the border you have T, I, J, and J equal to the external T for every x belonging to the dynamical part of B star, of the surface of B star. And then T of x is assigned for every x belonging to the kinematical part of the surface of this star. And this is the partial differential equation. Now, you see, first of all, how many equations we have for the whole body? We have an equation for I equal to 1, an equation for I equal to 2, and an equation for I equal to 3. So we have 3 equations and some boundary conditions. But the fields to be seen here are 9 because T is a general tensor, have 9 components. So we need some constitutive equation that is the same to assign this E with respect to C. This function E with respect to C. I will skip how to assign this internal energy, because maybe dell'Isola will do, or I in the following lectures. And just to say that if I have a good assumption on E, most of the time, sometimes the tensor T has this form. This is equal to Q mu E Ij plus trace of E, that is H delta Ij lambda. This is a way to assume a form for T with respect to what? With respect to the displacement. Because E is assumed to be the following: 1/2 the derivative of U I with respect to xj plus the derivative of uj with respect to xi. In the linear case, almost. In the linear case, first of all, you see that T is symmetric. The first Euler-Kirchhoff stress tensor is symmetric. Because I and j can be changed because this is a symmetric tensor, and also this is a symmetric tensor. So in this case, so E is defined as follows, and T is defined as follows. If you put this inside there, you have now always 3 equations, but now into the 3 unknowns that are the 3 displacement components. Let us now have an example in the same way we did when I came here this time yesterday. For example, if I have x1 equal to capital X1 plus epsilon x1 and x2 equal to capital X2. First simple example. What does this mean? Means that u1 is equal to small x1 minus capital X1. That is epsilon x1. And u2 is equal to 0. If you define h as the derivative of the component of another matrix, Hij as the derivative of ui with respect to xj, you see that E is nothing else than the symmetric part of E of H, because E is equal to 1/2 H plus H transport. But here the matrix H, what is it? The first component, component 1 is equal to the derivative of u1 with respect to x1, that is epsilon. The derivative of u1 with respect to x2 is 0, and 0 also the other component. E is nothing else than 1/2 H plus H transport. This is symmetric, so it is equal to E in this case. And so we can also say how much is T. How much is T? T is 2 mu mi H, so this. So we have 2 mu epsilon plus so this component is the component 1,1. We have to see to put it here 1,1. So here we have 2 mu E11, that is epsilon, 2 mu epsilon, this one, plus the trace of A of E, that is epsilon plus 0, so plus epsilon, that is the trace of E, delta 1,1, that is 1, multiplied by lambda. Here we have 0, 0, and 0. Let us see now if the first partial differential equation is satisfied. Okay, epsilon is a constant. Lambda and mu are constant. So this equation is if with no weight, if with no volume force, so with no B, this equation is satisfied because T is constant. B is 0. If B is 0, I mean, that partial differential equation is satisfied if B is 0, because T is constant, so the derivative of T is 0, and so B is 0. But what about the external force? Now we have to go a little bit deeper. Because let us assume that here we have a square plus last time. Here, you remember that this was x1, this was x2, and in order to keep rid of this, placement, this square, our body is enlarged, is elongated in one direction. So let us now say, and now we assume that, let us see how much is the force here. How much is the force here? First of all, we have to prescribe the kinematics. Let us prescribe this kinematics. So we prescribe that this surface is fixed, but it is fixed only in this direction. So we get, this is a square, we impose only that the displacement in the x1 direction is 0, but the displacement in the y direction is free. We see how. I have to be more precise, because if I impose a displacement, in fact we impose the displacement in all the body. We impose the displacement in all the body. But now we can see how much is the force that we have to apply at the surface in order to have this displacement field. And we will see some strange things. Why? Because now, let us see how much is the force here. How to evaluate the force here? We have to evaluate T applied to M. This is the area. I have to apply this tensor to this normal vector. We can see that in this surface, the normal vector is this one. We can say that this normal vector has only a component in the x1 direction and 0 component in the y direction. That means that in the x direction the component is 1 and in the y direction the component is 0. That means that here we have an external force that is equal to this multiplied by this. So we have so 2 mu epsilon plus lambda epsilon 0, 0, 0 applied to 1, 0. And this is equal to this multiplied by this plus 0 multiplied by 0. That means lambda epsilon to 2 mu epsilon 0. That means that in order to have this displacement, I have a force only in this direction. Let us see now what is the force in this field, in this surface, in in this surface, the normal is this one. Maybe I call it M. This M is equal to, in the x direction, the component is 0, in the y direction, the component is 1. So the external force now is this one. 0, 1, 0, 0, 0, 0, it's 0. There is something wrong because I have displacement only in one direction. We have this. Here I have a mistake. Let us correct what I said before in this part. So I have that U1 equal to epsilon, LZ, and U2 equal to 0. Do you remember? Now H is epsilon, this is epsilon S1. So this is epsilon 0, 0, 0. So T is equal to 2 mu E plus lambda trace of E multiplied identity. That means that the component Tij is equal to Q mu Eij plus lambda EH delta Ij. So the component 1 is correct because it is Q mu equal 1 or epsilon 1 or H11, so Q mu this plus trace of A multiplied by lambda. In the out of diagonal term, delta Ij is 0, Eij also is 0. The mistake is on this part, because in this part I have lambda EHH, that is the trace of E, that is epsilon, lambda epsilon, multiplied by delta 2, 2. That is 1. So T is this one. That means that here I have a lambda epsilon. That means that when I have 1, 0, so in this part there is no problem because I have almost in the first component I have 2 mu epsilon 2 lambda plus lambda epsilon multiplied by 1 plus 0 multiplied by 0. Second component I have 0 plus 0. So it is true that in this border I have only a force in this direction. In this border, however, I have this normal vector, so the external force is equal to Q mu epsilon plus lambda epsilon 0, 0 lambda epsilon, 0, 1. That is 0, 0, 0 lambda epsilon. What does it mean? It means that in order to elongate this square, only elongate this square, I need not only a force in this side, but also a force in this side. In which direction? In the orthogonal direction. Because naturally, a material, when you elongate, is restricted. If I impose, however, that I have only a deformation in this direction, so no deformation in the y direction, in the x2 direction, it means that I have to use some constraint. I have to apply some force in order to have only one elongation. If you take a piece of elastic, or square elastic, and you elongate, you will see every time that this is restricted. But here, I have imposed this displacement function. So I have imposed u2 equal to 0. That means no restriction. It means that if you don't want to see the restriction, you have to apply some force. How much is this force? Lambda epsilon. And this is so-called Poisson effect. And then you can also use some. Okay, this is a direct problem. You have a displacement, and you calculate the force in order to have that displacement. This is a problem that is called inverse problem. That is quite easy because you have only to integrate. You have the displacement. Sorry, you have only to make derivative. You have the displacement, make derivative, and you see the external action in order to have this displacement. The problem that is more difficult is when you have the force and you don't know the displacement. Because in this case, you have the force, you don't know the displacement, you don't need to derivate, but you need to integrate. And generally, the integration is more difficult than the derivation. And then you can use, or you are lucky and you find the analytical solution, or you use console, as in the next week. Ivan will teach you how to do with the software. Another displacement that is nice to investigate is the shear displacement. If I have a square that is that we want to displace in this way, how to model this? We can say that in u in the one direction is 0 when this is x2, this is x1, is 0 when x2 is equal to 0, and as far as x2 is increased, u1 is increased. So we can say this is x2 multiplied by gamma. And u2 equal to 0. What is changed now? Is changed that h is not anymore this, because h is the gradient of u, is the gradient of u. So the first component is the derivative of u1 with respect to x1, that is 0. The component 1, 2 is the derivative of u1 with respect to x2, that is gamma. Second line is 0. it means that E is the symmetric part of this. So it is 0, gamma of alpha of gamma 0. So here the trace of E is equal to 0. So this part is 0. Remains the first part. So in the first part, it's simply we have so 0 gamma mu and 0. This is T. What does it mean? That here we have 0 gamma mu 0 gamma 0. So in this border, the normal vector is 1, 0. So it is this one. And we have 0, 0. And then we have gamma mu 0. It means that in this border we have to apply a force in this direction. So the displacement is 0 here and revolve here. Correct. And in this side, the normal is now 0, 1, not anymore 1, 0. So we have here mu gamma and 0. It means that in this part you have to apply a force in this direction. This side you have to apply the force in this direction, and in this side you have to apply the force in this direction. It means that in order to have this shape, this is your square, you have to apply this force and this force. The fact that we have to apply both is related to the fact that this Cauchy stress tensor, this viola stress tensor, is symmetric. And it's something to do with the balance of angular momentum, because you cannot have only a force in this way, otherwise you have a rotation, but you have also to have a force in this way. Of course, in the other side, what is the external normal in the other side? The stress tensor is the same. What is the external normal here? Here, the external normal is 1, 0. Here, because it is this one. Here, what is the external normal? What is the external normal? 1, 0. So 1, 0, it means that there's a component 1 in the x1 direction and 0 component in the y direction. So this is the normal on this side, the external normal on this side. In this side, the external normal is this one. So the component is not 1, 0, but minus 1, 0. If it is minus 1, 0, and t is the same, it means that the external force is opposite. So in this side, you have this relation, and the same if here the external normal is 0, 1, here the external normal is 0, minus 1, and so the external forces are opposite. You see that the deformation of this square is in fact this this shape. And then if you rotate, you have this shape. Because this procedure does not get rid of the rigid body rotation. When you see this constitutive equation, you don't see rigid body rotation. Rigid body rotation is assigned by some kinematical constraint. Okay? I think that it is enough. I think that it is enough. Do you have some questions? Some curiosity? So we have derived partial differential equation for a phase gradient material in which the internal energy depends on C. If you want to get rid of material with higher order gradient, you have to consider different constitutive equation for E. But then you can see that because we make this derivation by parts, here C we have only one derivative with respect to x. If you want to consider second graded material, so material like this, you have two derivatives with respect to x, so you have to make integration 2 times, integration by parts 2 times. So the boundary conditions are more complicated. You don't have only force, but also other things that are called in the literature double force. And also the kinematical constraints are not only imposed in terms of displacement, but also in terms of grade of displacement. But here we have only first graded material, so I think that is enough. If you don't have another question, we can stop. Okay?